How does an airplane generate lift? I mean, really, how does this actually physically happen? Some of us have wondered this as we've looked up at the sky to see a soaring Boeing commercial airliner. We all know lift comes from the wings. Wings generate lift pushing the airplane upwards, while the forward movement of the plane is generated by a thrust force, which is provided by an engine. And competing with the lift force is the weight of the plane, and competing with the thrust force is the drag on the plane. But this two-part lesson is on the generation of lift and how low-speed airplanes are able to achieve it. The goal is to give you a fundamental understanding of the physical mechanism responsible for creating lift on an airplane wing by studying from basic principles the flow over a two-dimensional cross-section of a wing called an airfoil. Resorting to the study of 2D flow greatly simplifies the analysis. And although the flow over a 3D wing is slightly different than the flow over an airfoil, the nature of lift is still captured in the analysis of the 2D flow over an airfoil. But before we can even talk about the flow over airfoils, we first have to focus on a few things to set up the analysis. In part 1 of this lesson, we'll deal with this background material. In part 2, we'll go into more details on the theoretical analysis of lift over airfoils for low-speed applications. So let's first talk about our basic assumptions. Most single-engine turboprops cruise around 100 to 130 miles an hour. And this is slow enough to assume that the entire flow field around the plane is at a constant density. Now, this isn't true for flows where the speed of the aircraft approaches the speed of sound. At Boeing 777 cruising speeds, the air moves so fast that there is a significant change in density as the velocity and pressure change over the wing. For this lesson, we'll ignore compressibility and assume we're at low-speed flows. Therefore, we're assuming what is called incompressible flow, and this just means the density of the air in the flow does not change. Now, this isn't the only assumption we'll make. We'll also assume that the viscosity of the fluid does not affect the flow field. In fact, viscosity has little effect on lift, while having a much greater effect on the drag of an aircraft. Inviscid flow is also a safe assumption for determining lift because even though the flow around the wing isn't fast enough to cause compressibility effects, it is fast enough to dominate over the viscous effects caused by air dragging across the surface of a wing. The magnitude of the viscous effect can be estimated by looking at the Reynolds number. The Reynolds number is just rho times V times L over mu. Rho is the density of the fluid, V is the velocity of the fluid, L is the characteristic length of the flow, which we'll take as the chord length of the airfoil, and mu is the viscosity of the fluid. Using the density and viscosity of air at sea level, a speed of 110 miles an hour, and a chord length of 1 meter, the Reynolds number is about 7 million. Such a high Reynolds number means that the viscous forces are completely dominated by the inertia of the fluid. So much so that all the viscous effects are smushed down to a very thin region at the surface of the wing called the boundary layer. This means that nearly the entire region around an airfoil can be analyzed assuming incompressible, inviscid flow. Now this greatly simplifies the momentum equation of the flow to the form known as Bernoulli's equation. Viscous forces are eliminated from this equation, and all that's left is the exchange between the pressure and the inertia of the fluid. Now, if we follow a streamline from the free stream where pressure and velocity are known, and here we know the pressure is just the surrounding pressure of the atmosphere, and the velocity is just the speed of the aircraft, then we could rearrange our Bernoulli equation to find the pressure at another location we'll just label as star, given that we know the velocity at that star location as well. And if we pick the right one, we can actually follow the streamline that winds up flowing right against the surface of the airfoil, just above the boundary layer. So with Bernoulli's equation, we can extend this concept to calculate the pressure along the entire top surface of the airfoil. If we then integrate this pressure distribution over the top of the airfoil, we can determine the value of the pressure force acting on the top surface. We can apply the same idea to determine the pressure force along the bottom surface of the airfoil. With the pressure distribution over the top and bottom of the airfoil, we can determine the aerodynamic lift and drag forces on the airfoil. So with this method, we know we can calculate lift and drag on an airfoil if we know the velocity field. But this leaves us where we still need to determine the velocity field. Once we obtain the velocity field, we can use the Bernoulli equation to calculate the lift. Luckily, we have another equation that we can use besides the momentum equation, known as the continuity equation. The continuity equation for 2D incompressible flow is simplified to du dx plus dv dy equals 0. Also, because it is 2D and incompressible, we can use the stream function psi. The stream function is related to v and u as shown, where v is negative d psi dx and u is d psi dy. Plugging these into continuity, we see that the terms cancel each other out, which validates the usage of psi for 2D incompressible flow. Since we are also assuming Inviscid flow, the flow is irrotational, which means that dv dx minus du dy equals 0. Plugging the psi values in, we get Laplace's equation, which is just d squared psi dx squared plus d squared psi dy squared equals 0. We now have an equation that represents the entire flow field in terms of only one variable, psi. This is a lot easier to deal with than having the continuity equation with two variables to solve for, u and v. The continuity equation in terms of u and v was a partial differential equation, much harder to solve than Laplace's equation, which is an ordinary differential equation. Even though now we have the differential equation, we're not actually going to solve for psi like you normally would solve a differential equation by integration or separation of variables or some other method. We're actually going to use known solutions of psi for simple elementary flows. We can actually add these solutions together to form flows over more complex geometries. It's important to remember that the addition of the solutions is only permitted because the governing equation is linear. Our first elementary flow to look at is uniform flow, which is just straight flow in the positive x direction. So the u velocity is equal to v infinity, and integrating u with respect to y gives us the stream function v infinity times y. And the constant of integration is arbitrary, so we just set it to 0. Cylindrical units are typically more appropriate when analyzing flow over round bodies, so psi can also be written in cylindrical coordinates. Our second elementary flow is called source flow. It represents flow out of an infinitely small point, the flow emanating in all directions radially from that point. The radial velocity gets smaller as you move away from the origin, and the velocity in the tangential direction is 0. And this may seem physically unrealistic, but it will actually help us build flows around cylindrical bodies later. The opposite of a source is a sink, where the flow all converges to one single point. The only difference is that the radial velocity, and hence the stream function, is now negative. Our third elementary flow is called Vortex Flow. It represents flow that swirls around the point origin. And this time the velocity in the radial direction is 0, and there's only velocity in the tangential direction. And the tangential velocity gets larger as you move away from the origin, such that the flow remains irrotational. The gamma is the strength of the vortex, and it's also known as circulation. Note that the flow is clockwise for positive gamma. Now here's where it gets interesting. If we add the uniform flow and a source flow together, we get what looks like flow over a blunt-nosed body. The uniform flow pushes over the source flow and causes all the fluid to move to the right. Notice the bold streamline. This streamline forms the surface of the blunt body. Since the flow inside the blunt nose body is completely separated from the flow outside, we can use this as a model of flow over a blunt body by ignoring the flow on the inside and just focusing on the flow on the outside. We can also increase the strength of the source to make the body wider or decrease the strength to make the body thinner. Now let's add a sink to this flow to the right of the source. The sink has the same strength as the source, so it's able to completely close the end of the blunt body. And now we have flow over an ellipse. All that we had to do was add the stream function of a sink to this flow. Note that the stream function of the source and sink are a little more complicated because the origin of the flow is in the middle of the ellipse. Now with this stream function, we can easily calculate the radial and tangential velocities around this ellipse with the definition of the stream function. And from there, we can use Bernoulli's equation to calculate the pressure field around the body, and then integrating that pressure over the surface, we can determine the lift and drag. One could imagine that blunt bodies of any shape could be created by combining multiple sources and sinks together at different locations. Now we're starting to see the power of combining these elementary flows to form flow fields around practical objects. Now let's bring together the source and sink so that they're infinitely close to each other. When we do this, we get flow over a cylinder. It may seem weird right now that we're studying flow over a cylinder instead of flow over an airfoil, but this analysis will actually give us great insight into the nature of lift. Note that the source and sink flow are combined to form what's called doublet flow, which has its own stream function where K is the strength of the doublet. The stream function can be simplified because R equals K over 2 pi times V infinity. Again, we want to ignore the flow inside the cylinder and only focus on the flow on the surface and outside of the cylinder. Now, if we want to find the lift on the cylinder, we first must know the velocity on the cylinder surface. So we set the R coordinate equal to the radius of the cylinder, big R, so that the radial velocity VR is 0 and the tangential velocity V theta equals to negative 2 V infinity times sine theta. And it makes sense that VR is 0 because we expect no velocity to go in and out of the surface, no injection or suction. Now that we have the velocity field, let's turn to Bernoulli's equation to find the pressure field. We substitute in the velocity at the cylinder surface to get the following expression for pressure along the surface. To obtain the lift, we then integrate the pressure along the top surface directed vertically down. And we subtract that from the integration of the pressure along the bottom surface directed vertically up. And that's how we get lift. And notice that it's lift prime, L prime. That's the lift per unit span because we're a two-dimensional problem here. And carrying out this integration is not difficult, but it does require a lengthy expression. So I'll just give you the end result here. That when you carry out the integration, all the terms cancel and the lift is 0. And we expect this. No one would really think that the plane cylinder could generate lift by itself. There's no curvy shape to it like you see on an airfoil. And if you look at the streamlines, you can see why. The streamlines above the cylinder and below the cylinder are mirror images of each other. Now, since the velocity distribution on the top surface of the cylinder matches the velocity distribution on the bottom surface, the pressure distributions must also match, just by Bernoulli's. So if there's no pressure imbalance between the top and bottom, there's no pressure, no net pressure force, and thus no lift. In order to make asymmetrical velocity distributions, we can add a vortex flow to our cylinder. Notice we added here a clockwise rotating vortex, meaning positive circulation. This represents a case where we're rotating the cylinder clockwise. The streamlines above the cylinder no longer match the streamlines below the cylinder. Again, we set our R coordinate to big R to get the velocity along the surface of the cylinder. Here, VR is still 0 to be expected, and V theta actually now equals negative 2 V infinity sine theta minus the new term gamma divided by 2 pi R. Now from the Bernoulli equation, the pressure then becomes the long expression seen here. And when we calculate the lift, we now get a non-zero value. There is lift here because the fluid is moving with a faster velocity over the top of the surface, the top of the cylinder, than it is over the bottom of the cylinder. That, in essence, is the reason wings have lift. The airfoils are shaped in such a way that the velocity is faster over the top surface than it is over the bottom surface of the airfoil. And a higher velocity results in a lower pressure, so that the pressure on the top is lower than the pressure on the bottom, and therefore a net pressure force pushes the wing upward. Now here we're not using the shape of the cylinder to create lift. We've already seen that the shape doesn't create lift, but here we create the faster velocity along the top surface by rotating the cylinder in a clockwise way. So note how the lift per unit span actually comes out to be a very simple expression. It's only rho times V infinity times gamma. And it turns out that this expression for lift isn't just applicable for a rotating cylinder. It applies to the incompressible Inviscid flow over any two-dimensional object. It's called the Kutta-Joukowski theorem. And it means that for every airfoil, this equation holds, no matter the shape of the airfoil. So different airfoil shapes have different values of circulation to give them different lift values. Note that this doesn't mean circulation causes lift. Remember, it's the imbalance of the pressure forces on the top and bottom surfaces that physically cause the lift to happen. Circulation is a byproduct, and it happens to have a nice, simple relationship with lift that we can take advantage of. Now, because the Kutta-Joukowski theorem is such a simple relationship between lift and circulation, it's common practice to represent airfoils as simply a line of connecting vortex flows, also known as a vortex sheet. As shown here, the surface of the airfoil is replaced by connecting vortices, which are drawn as points with circling arrows. The strengths of the vortices are not all the same as each other. They're all solved for simultaneously so that the induced velocity field, when you add it to a uniform flow, produces a streamline of the flow that matches the shape of the airfoil. The total circulation is just the sum of all these vortices, the sum of the circulation of all these vortices. The lift per unit span is then calculated from the Kutta-Joukowski theorem. And if the total circulation has a net positive value, then we have lift. Now, if the total circulation has a negative value, then the force on the airfoil is actually downwards, like you would see with a spoiler. And this results in a negative lift, obviously. This simple technique of using a vortex sheet to simulate the flow over an airfoil and then use the Kutta-Joukowski theorem to calculate lift has been successfully used by aerodynamicists in the past to design and optimize airfoil shapes that produced high lift. I'd now like to summarize this part 1 lesson. We first assumed our flow could be treated as incompressible and inviscid. This allowed us to use Bernoulli's equation, the stream function, and also allowed us to add together elementary flows like the uniform flow, the vortex flow, and the source flow to create interesting flow patterns. We then learned that through studying flow over a rotating cylinder, that the cause of lift was the asymmetry of the velocity field around the cylinder. And through Bernoulli's equation, this gave a net imbalance in pressure, which resulted in a non-zero lift force. This mechanism was the same way that airfoils obtain lift. We then learned that Kutta-Joukowski theorem allowed us to calculate lift from any flow with a known vortex strength. And this makes it a useful tool for designing high lift airfoils. Now in part 2 of this lesson, we'll go more into the quantitative analysis of flow over airfoils. And we'll do that by studying classical thin airfoil theory. And so with part 1, we sort of got us halfway there by building our fundamentals. And part 2 now we'll get to study the nitty-gritty details.